All right, back to our meter stick example. Let's say that we place a 200-gram mass 50 centimeters to the left of the origin. And in this case, I'm going to call this origin right here, this is going to be 0 centimeters. Now, in our lab, that was 50 centimeters, right? That mark on the meter stick was the 50 centimeter mark. That was where you were measuring from. So I'm just going to call that 0. Again, it's arbitrary. You can call whatever point you want here 0 on your number line. We're just going to measure everything relative to that point. So I know that this mass here is 200 grams, and I'm told that it's 50 centimeters to the left of the origin. So I'm going to go ahead and just annotate the diagram as I go. A 25-gram mass, so this mass 2 here must be 25 grams, is placed, let's see, 10 centimeters to the right of the origin. So R2 here is going to be 10. And then a 100-gram mass, so M3 here will be 100 grams, is placed 40 centimeters to the right of the origin. And again, I've defined that to be the middle point. So find the position of the center of mass. The center of mass may not be at the point of rotation or at that middle of the meter stick. It might be somewhere else, right? And that's what we're going to calculate. Remember that the equation for the center of mass, I can calculate the center of mass by multiplying all of the masses and their positions. So I'm going to say that'll be M1 times, and I'm actually not going to use R here. I'm going to use the X, like the position of that mass, because R is the distance, but this is just the position. M2 X2 plus M3 times X3. Okay, and I'll divide that by all of the masses added together. If I had 4 masses, I would have 4 terms. If I had 5 masses, I'd add all 5 terms. But again, I only have 3, so I only have 3 terms here. Then I need to just decide what each of those X values are going to be. Well, if the distance from the center for this first mass is 50 centimeters, and I'll say that this mass is over here at the, right, this will be X1 equals negative 50 centimeters. So I'm thinking like a number line. If this is 0 and that mass is 50 centimeters to the left of 0, then it's going to be at the position of negative 50 centimeters. Same thing for mass 2. If mass 2 is 10 centimeters to the right of 0, that will be, so the X value for mass 2, right, will be 10, positive 10 centimeters. And same thing for mass 3. X3 would be positive 40 centimeters because it's 40 centimeters to the right of my 0 point. So I'll go ahead and plug in all these values into my center of mass equation. All right, and so once I've plugged in all of my masses and position values, I'm going to go ahead and put that into my calculator, and I will get a position of negative 17.7 centimeters. And so what this is telling me is that my center of mass of the meter stick and mass system is 17.7 centimeters to the left of where I defined the origin to be. So it would be somewhere right around here maybe. So this would be my center of mass. And so what I could do, if I didn't want to move the masses around to try and get that center of mass in the actual center where I've attached it to the rope, what I can do is I can just move the whole meter stick to the right 17.7 centimeters with the masses attached as they are, and it would balance. So if I were to move the center of mass to the center of rotation, or where I've actually attached the string to the meter stick, I could just slide the meter stick to the right and it would balance just like that. So you can either move the masses around such that the center of mass is actually where you have the string attached, or the geometric center of the meter stick, or you can move the meter stick and mass assembly such that the center of mass is positioned where the string is. This concludes a series of videos on center of mass. Thank you for watching.